Welcome to the last video of this series where we were writing a DPD simulation. Remember, DPD is dissipative particle dynamics. It's a coarse-grained simulation technique. We were writing a DPD simulation from scratch in C to simulate some polymer systems. And what I did is, after the last video, I took our completed code, which is now available on GitHub for you to check out, took that code, ran a couple of simulations for a couple of different systems to look at whether or not the results of our DPD simulation make sense, keeping in mind what we know about polymer physics, right? Knowing about our kind of classical polymer physics theories. So I ran 3 different types of systems, which amounted to what? 1, 2, 3, 4, 5, 10, 11 different simulations. The first one I ran was a set of simulations that had a 5% by volume component of polymer, and I varied the chain lengths, and of course the rest of it was then solvent, so 95% of the volume of the system was solvent. And I did it such that Aij was equal to Aii was equal to 25, so the strengths of the interactions between all of the different components, polymer-polymer, solvent-solvent, and polymer-solvent, were all the same strength. And what I expect based on our knowledge of polymer physics is that the radius of gyration should scale as the degree of polymerization to the 0.588 power in 3D. Actually, it's not the degree of polymerization here, it's the number of segments, so it's the number of bonds. Of course, if the degree of polymerization is like 1,000,000, then the difference between n and n-1 is, negligible. However, for our simulations, because our chain lengths are a maximum of 100, I did subtract off 1 from the degree of polymerization to look at the scaling relationship, and we'll see what came out from that. Second system I ran was a polymer melt, and these are relatively short chains, so this is the case where there's no entanglements, and of course entanglements don't affect what we're looking at here. We're looking at the scaling of the radius of gyration, but I do want to mention that there are no entanglements. And I ran it for the same set of degrees of polymerization, and we would expect that Rg would scale as n to the 1/2 power here. In the solution, we've got excluded volume effects that cause the chain to be a little bit bigger than we would expect for a freely jointed chain. That's captured by Flory's theory, for example. But in the melt, where we have no excluded volume for our system, we would expect to recover the freely jointed chain result. And then finally, I looked at a binary mixture of immiscible fluids. So I kept the degree of polymerization of the A component to be 1 here. And I looked at 50% A and 50% B. So just a 50-50 mixture of 2 different fluids. And in this case, I set the interaction Aij to be 100. So the interaction between different types of particles was much more repulsive than that of similar type particles. And we'll see what that gave us. Just as a note, this kind of system here is what got me started in polymer science. And so I'm kind of going back 20-something years now to where all of this started. So let's see how this came out. What I'm showing here on the left-hand side, I have the movie that I rendered in Ovito of one of these simulations. And this is of the polymer solution where the chain length was equal to 100, and again at 5 volume percent. And it's kind of hard to make heads or tails of it, because really we've just got a bunch of particles that are bonded to each other flying around in solutions. There's not much useful information to be had from this video. What is useful is we tracked the radius of gyration of the polymer, the root mean squared radius of gyration of the polymers, as a function of time. So this is the time step multiplied by dt, or delta t. And you can notice a couple things. First of all, that the radius of gyration equilibrates to a more or less constant value relatively quickly. So for n equals 10, 20, 30, 50, and 100, we see the radius of gyration increases as the chain length increases. Another thing you might notice is that the fluctuations in the radius of gyration start to increase as we go to longer and longer chain lengths. This is not because anything funky is going on, but this is just because we've got fewer polymer chains for n equals 100 than we do for n equals 10, because we're keeping the size of the system fixed and the volume fraction fixed. If we were to look at similar numbers of chains, we would probably observe that the fluctuations of all these systems would look the same. So for analyzing this, what I did is I fit the data to a straight line at these different values, looking at the region where the radius of gyration seemed to have reached some steady state value, And I took that to be the average radius of gyration for the simulation, right? Because it's fluctuating over time. In practice, this is not how I would do it. In practice, what I would do is I would look at what the average radius of gyration is. Well, I could do it a couple ways. I could look at what the average radius of gyration is once it's equilibrated and average that across several independent runs of my system. The other thing that I could do is, instead of that, kind of equivalently, I could run this simulation a couple of times so that I get a different random seed every time, and then average together the radius of gyration as a function of time, and then look at what that is. So I'm just saying this to point out that what I'm doing here is not what I would do if I was doing an actual study that I was going to submit for publication and things like that, but it's good enough right now to check whether or not our code behaves. And so that's what we observe for solution. In the melt, well, there's even less to see in the video because 100% of the volume of the system is occupied by polymers. You'll notice that the fluctuations in the radius of gyration have decreased a little bit. You'll also notice that the n equals 30 system is missing because I forgot to run it, but you're welcome to do that. You'll see that we have enough data here to get a decent fit to our data, a decent fit to the radius of gyration data that I'm about to show you. But we observe the same general trends. As the degree of polymerization increases, and we see an increase in the radius of gyration. The size of the fluctuations in RG have gone down because we have more polymer chains in the melt than we did in solution at 5 volume percent. And so that's what we get. So we can get the average values of all of these radius of gyration and see what they give us. So here we go. I'm plotting the summary of that data. So I'm plotting the average root mean squared radius of gyration, which is kind of an odd way to say that, but I'm plotting that as a function of the number of segments. So the degree of polymerization -1, that will be the number of bonds in the system. The error bars here are just the uncertainty, the standard error, let's say, in the linear fit that I did. And you can see that the error bars are very small. They're smaller than the size of the points that I've chosen here, and that is what it is. So what you're seeing are power law fits to the data. Squares are the solution data, and circles are the melt data. And the results of those least square fits is that the radius of gyration in solution scales as the number of segments to the 0.57 power. That is incredibly close to the value that we know from renormalization group theory approaches. So that's good. Our simulation reproduces good solvent conditions. And for the melt, we find that the radius of gyration scales as the number of segments to the 0.5 power, which is exactly what we would expect for a freely jointed chain. So in terms of our polymer solutions and polymer melts, our DPD code generates the correct results in terms of the radius of gyration. And that's really all that we've calculated here. Finally, I'm showing here a binary mixture of immiscible fluids. We've got n equals 1 here. So again, just simple fluid, no polymer chains. You would observe the same thing for polymer chains, except the dynamics would be a little slower. And I'm showing you what I did to the interactions to get that phase separation. And I'm just saying that if Aij is larger than Aii, that's implying that AB contacts are not favored. So what we would expect and what we see in the movie is that as time progresses, we get a complete phase separation with all of the A particles or with all of the A particles. Mostly. Of course, you're always going to have some limited solubility. All of the B particles, which I'm not rendering here, are with all of the B particles. And we're minimizing the surface area. And so in this case, the minimum surface area would be two flat planar interfaces. And we're seeing some fluctuations in the interface. So our code is correct in terms of a binary mixture of immiscible fluids. And so it looks like everything is working really well here. And so the code works. We've verified it for these simple cases. And so the question is, well, okay, what next? So here's some ideas that you can do. I'm not going to do them. This is the last video of the series. What we simulated was a linear homopolymer separated, or where the bonding is taken care of by a harmonic potential. You could expand upon this to create a star polymer. So I'm showing a star polymer. Every bead is the same type. So it's a homopolymer, I guess. It's a star polymer with 4 arms. Okay, I'm not showing, of course, the other monomers out here. So you could modify the code to stimulate star polymers. You could look at mycto-arm polymers where the different arms have different chemical identities. You can look at block polymers. So I'm showing down here a linear diblock copolymer where the fraction of A is equal to the fraction of B. So we've got 50% A, 50% B. And we could simulate that. And the way that we would do it is we would calculate how many monomers of the polymer chain would correspond to p-type equals 1. If you remember, that's where in the code we set the species or the particle type. And then once you go over that number that you've calculated, so for a polymer chain of 6, obviously 50% would give you 3 of the beads would have to be polymer type of 1. And then after that, the remaining beads would be polymer type -1. You could look at statistical copolymers, random copolymers. You could look at any number of things, right? That's just one example. You could look at immiscible polymer melts. You could modify the code so that you do what's called core modified DPD. So for example, in the case of the star polymer, you could take that central monomer of the polymer and make it a much larger bead. And then you could start simulating polymer grafted nanoparticles, at least those that are spherical, or any number of things, right? There's more that you can do than just these couple of suggestions. In fact, here are some other suggestions. We implemented bonding in this code by looking at the harmonic potential, largely because it's the easiest way to do this. But there are other potentials that are commonly used. The most common one in my experience is FINI, the finite extensible nonlinear elastic potential. And it's given by this formula here. So if your separation distance between adjacent monomers is less than R max, then the potential is given by this function here. Otherwise, the potential is infinite. Okay, so I'm comparing the two functions here in this plot. The black line is the harmonic potential for a spring constant of 40 and an equilibrium bond length of 0.7. I'm comparing that to the FINI potential, which shoots up to infinity right here. And it's got a similar strength, so it's got a force coefficient over here of 40. R max was set to 2, and the equilibrium bond length was set to 0.7 to kind of match the harmonic potential. And you can see that it's a much steeper, a much stronger bonding potential than the harmonic. So you could implement that if you wanted to. Some final suggestions. As we've written it here, DPD cannot simulate entangled polymers without modifications. So if you wanted to look at things like reptation, the code that we wrote won't do it. You would have to add some functionality, and it exists. For example, a repulsive potential between segments. I forget what that's called exactly, but there's some papers in the literature where you do this segmental repulsion and you could simulate entangled polymers. You can put in checkpointing. So right now, if your simulation was interrupted, if your computer crashed, or if you're running this in an HPC environment and you ran out of time for your job, what you've done is lost other than the data files that you have. So can you write out all of the forces, velocities, and coordinates so that you can load them back in and pick up your simulation where you left off? So that's called checkpointing. The code that we use for our research uses checkpointing, and it's really helpful. You could implement Rouse mode analysis to calculate relaxation times. So you could study not only the structure of your polymers, whether they're in solution or in the melt, but you could study their relaxation dynamics. So you could see whether or not the Zim model applies to your polymer solutions, whether or not the Rouse model applies to your polymer melts, your unentangled polymer melts. I've done this before with DPD, and it turns out that yes, it does agree with those. The dynamics do agree with those classical theories. Something I've been interested in recently is not doing Rouse mode analysis, but doing proper orthogonal decomposition of the fluctuations in the monomer positions to figure out what the modes are, and they should match the Rouse modes for linear chains, and then using those to calculate normal coordinates and then look at relaxation time. So this is a more general method for analyzing dynamics that agrees with Rouse mode analysis in the limit of linear chains. So you could implement this. Or there's several opportunities to optimize the code as we've written it. So do fewer operations per time step. Or you could parallelize it using OpenMP, which is pretty easy to do. You have to be careful about thread safety and not having any race conditions. Those are things where you can start to overwrite data and get incorrect results. But as long as you do it properly, you could parallelize this with OpenMP so you can use more than one CPU core, or any number of things. So I hope that this video series, as brief as it was, has given you some insight into how to write your own code that does DPD, as well as some suggestions for some extensions you can make to the code so that you can start to apply this to other research problems.